Tonight, we're going to explore the true scale of Andromeda. You've probably heard it's the nearest large galaxy to us, the one that's going to collide with the Milky Way in a few billion years. But here's what most people miss. Every few years, astronomers revise the size of this galaxy, and the number always gets bigger, never smaller. It's happened enough times now that some researchers wonder if we've actually found its true edge at all. Andromeda is already known to be more than twice the width of the Milky Way, holding an estimated 1 trillion stars, sitting 2.5 million light-years away. By the end of tonight, you're going to understand exactly why this galaxy keeps outgrowing every measurement we throw at it, and just how far its true edge might actually reach. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the sky itself. On a clear autumn night, away from the glow of streetlights, you can find Andromeda without a telescope. It sits in the constellation of the same name, north of the Great Square of Pegasus, and with just your own eyes, it looks like nothing more than a soft haze. Ancient astronomers noticed it too. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 in his book of fixed stars, calling it a little cloud. He recorded its position carefully, alongside the other fixed points of light he catalogued that night, with no way of knowing that the little cloud he was describing was itself made of over 1 trillion suns. For nearly 1,000 years afterward, nobody knew what that cloud actually was. It was catalogued, observed, sketched, and debated, but its true nature remained hidden. The first telescopic observation came centuries later, in the year 1612, when the German astronomer Simon Marius turned an early telescope toward it. He described what he saw as resembling a candle flame seen through a translucent sheet of horn, a faint, glowing patch with no visible edges, no individual stars, just a soft, diffuse light. Marius had no context for what that meant either. Telescopes at the time were crude, barely capable of resolving planetary detail, let alone anything as faint and distant as an entire galaxy. Over the following century and a half, astronomers slowly built catalogues of these faint, fuzzy objects scattered across the sky, mostly to avoid confusing them with comets. That was the primary scientific interest of the era. The French astronomer Charles Messier included it in his catalogue in the year 1764, listing it as the 31st entry. That's where the name M31 comes from, a designation still used constantly in astronomy today, even though we now understand the object behind that simple catalogue number to be almost incomprehensibly vast. For Messier, and for nearly everyone who came after him for the next century, it was simply another nebula, a cloud of gas, presumably similar to the other clouds of gas and dust known to exist within our own galaxy, just larger and closer than most. Early telescopes only showed a bright, blurry oval, and for centuries, astronomers assumed it was a nearby cloud of gas and dust within our own galaxy, something they called a spiral nebula. The word nebula simply meant cloud, and that's exactly what it looked like through the instruments of the time. A meaningful clue arrived in 1864, when the English astronomer William Huggins pointed a spectroscope at Andromeda for the first time. A spectroscope splits light into its component wavelengths, the same way a prism splits sunlight into a rainbow. And by examining that spread of light, astronomers can determine what an object is actually made of. Huggins had already used the technique on several known gas clouds within the Milky Way, and their spectra showed the telltale bright, narrow lines of glowing gas. Andromeda's spectrum looked completely different. Instead of the narrow emission lines of a gas cloud, it showed a smooth, continuous spectrum, the kind produced by the combined light of enormous numbers of individual stars blending together. Huggins didn't have the tools to prove Andromeda was a separate galaxy, but his observation planted an important seed. Whatever this object was, it wasn't simply glowing gas. It behaved like starlight. Photography added another layer of evidence. In 1888, the English amateur astronomer Isaac Roberts captured a long-exposure photograph of Andromeda, and for the first time, its spiral structure became visible, sweeping arms curling outward from a bright central core. The image was strikingly similar in shape to certain other faint nebulae already catalogued, and it raised an obvious question. If this really was just a cloud of gas within our own galaxy, why did it have such an organized, symmetrical, almost mechanical structure? Then, in 1912, an American astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, measured something that would later become essential to understanding not just Andromeda, but the motion of the entire universe itself. Slipher measured the spectrum of light coming from Andromeda and detected a blue shift, meaning the wavelengths of its light were compressed slightly compared to what would be expected from a stationary object. A blue shift indicates motion toward the observer, the same underlying principle behind the sound of a car engine changing pitch as it approaches you and then passes by. Slipher calculated that Andromeda was approaching us at roughly 300 kilometers per second, an extraordinary speed, and completely unlike anything measured for objects known to exist within our own galaxy at the time. It was the very first evidence, discovered over a century ago, that Andromeda and our galaxy were destined to meet. Slipher didn't fully grasp the implications at the time, because the fundamental question of whether Andromeda was even a separate galaxy hadn't been settled yet. But the measurement itself, that blue shift, that approach velocity, turned out to be remarkably close to the modern value astronomers still use today. Slipher's work extended well beyond Andromeda as well. Over the following decade, he measured the spectra of dozens of other spiral nebulae. He found something curious. Almost all of them showed red shifts rather than blue shifts, meaning almost all of them appeared to be moving away from us, often at far greater speeds than Andromeda's modest approach velocity. Andromeda, it turned out, was something of an exception, one of only a small handful of nearby galaxies actually moving toward us rather than away. Slipher's growing catalogue of these velocity measurements became an essential ingredient a few years later, when Edwin Hubble combined them with his own newly established distance measurements, the same technique he'd used on Andromeda. Together, they revealed an even larger pattern, that more distant galaxies were, on average, moving away from us faster than closer ones. That relationship became known as Hubble's law, and it remains one of the foundational pieces of evidence for the expansion of the universe itself. The discovery that space between galaxies is stretching over time, carrying galaxies apart from each other at a rate proportional to their distance. Andromeda, moving toward us rather than away, sits as a notable exception to that overall cosmic expansion. It's held on its collision course specifically because the mutual gravity between it and the Milky Way is strong enough to overcome the broader expansion pulling most other galaxies apart, especially given how close the two galaxies already sit within the local group. The tool that would eventually settle the entire debate came from an unexpected place: the meticulous work of an astronomer named Henrietta Leavitt. working at the Harvard College Observatory in the early 1900s. Leavitt studied a class of pulsating stars called Cepheid variables, stars that brighten and dim in a regular repeating cycle. By examining thousands of these stars in the Magellanic Clouds, she discovered something remarkable: a direct mathematical relationship between how long a Cepheid's pulsing cycle takes and how intrinsically luminous the star actually is. The longer the pulse period, the brighter the star's true luminosity. This relationship, now known as the period luminosity law, became one of the most powerful tools in the history of astronomy, because it meant that if you could identify a Cepheid variable anywhere in the universe and measure its pulse period, you could calculate its true brightness. You could then compare that to how bright it appeared from Earth to determine its distance. Leavitt's discovery didn't immediately solve the mystery of Andromeda, but it handed future astronomers the exact tool they would eventually need. That assumption that the universe was contained entirely within the boundaries of the Milky Way held for a very long time, and it took one of the most significant scientific debates of the 20th century to unravel it. In 1920, two astronomers, Harlow Shapley and Heber Curtis, held what became known as the Great Debate. The event took place at the Smithsonian Museum of Natural History in Washington, D.C., as part of a meeting of the National Academy of Sciences. And despite its dramatic name, it wasn't quite the direct, heated confrontation popular retellings sometimes suggest. Each astronomer delivered a separate paper on a related but broader topic: the scale of the universe. And only afterward did their conclusions about spiral nebulae, like Andromeda, emerge as the most sharply contested point of disagreement between them. The published papers that followed sparked years of ongoing discussion within the astronomical community, discussion that wouldn't be resolved by argument alone, but by the kind of hard, observational evidence Hubble would provide a few years later. Shapley argued that these spiral nebulae, including Andromeda, were relatively small and located within our own galaxy. Curtis argued the opposite, that they were separate, distant galaxies in their own right, what he called island universes. Curtis had a specific piece of evidence backing his position, drawn from his own observations of novae, those temporary stellar outbursts appearing within Andromeda and similar spiral nebulae. He noticed that novae observed within these spiral nebulae were consistently far fainter than novae observed elsewhere within the Milky Way. And he reasoned that if these objects were behaving the same way physically, the only explanation for that faintness was distance. The novae weren't intrinsically weaker. They simply had to be much, much farther away for their light to appear so dim by the time it reached Earth. It was a clever, indirect argument, but it relied on assumptions that weren't yet fully proven. And Shapley had his own evidence pointing the other direction, based on the observed size and apparent brightness distribution of the Milky Way itself. Neither side had the observational proof to settle it. That proof came a few years later from an astronomer working at the Mount Wilson Observatory in California, using the largest telescope in the world at the time. His name was Edwin Hubble. Hubble was looking for variable stars within Andromeda, applying Leavitt's period luminosity law directly, searching photographic plates night after night for stars whose brightness changed in that specific, predictable pattern. These stars pulse in brightness in a very regular, very predictable way, and the period of that pulsing is directly related to how intrinsically bright the star actually is. If you know how bright a star truly is, and you measure how bright it appears from Earth, you can calculate the distance to it. It's the same basic principle as judging how far away a lamp is based on how dim it looks, compared to how bright a lamp of that wattage should be. Hubble found several Cepheid variables inside Andromeda, and when he calculated their distance, the number was so large it left no room for doubt. Andromeda wasn't a nearby cloud. It was hundreds of thousands of light-years away, far beyond the known boundaries of the Milky Way. The announcement came in 1925, and it fundamentally reshaped astronomy. The universe wasn't just one galaxy. It was filled with them, scattered across distances so vast that light itself, the fastest thing in existence, took hundreds of thousands, then millions, then billions of years to cross the gaps between them. Andromeda was the proof. The single object that changed our entire picture of the cosmos. It's worth pointing out that Hubble's original distance estimate, based on the instruments and calibration methods available at the time, was actually too small, placing Andromeda at under 1 million light-years away. It took decades of refinement to arrive at the modern figure of roughly 2.5 million light-years. That refinement involved better calibration of the period-luminosity relationship, corrections for interstellar dust, and eventually direct measurements from space-based telescopes. Science rarely arrives at a final answer in one attempt. It arrives through repeated correction, each generation of instruments sharpening the picture left by the last. One particularly elegant refinement came in 2005, when a team led by astronomer Ignacy Ribas used a rare and unusually precise method: an eclipsing binary star system located within Andromeda itself. Two stars orbit each other so that, from our vantage point, one periodically passes in front of the other, dimming the combined light in a way that can be measured with extraordinary precision. The team carefully analyzed the physical properties of both stars in that pair, their temperatures, their sizes, and the details of how their light dimmed during each eclipse. That let them calculate the true luminosity of the system, independent of any assumptions borrowed from Cepheid variables. They could then compare that true luminosity to how bright the system appeared from Earth. Their result placed Andromeda at approximately 2,520,000 light-years away, remarkably close to figures derived from entirely different methods. And it helped cement the modern consensus distance of roughly 2.5 million light-years that astronomers still use today. Multiple independent methods converging on the same basic answer is exactly the kind of agreement that gives scientists confidence in a result. Another major refinement came from an unlikely source: wartime conditions rather than new instruments. During the Second World War, mandatory blackouts across Los Angeles, intended to protect the city from potential aerial attack, had the accidental side effect of dramatically darkening the skies around the Mount Wilson Observatory, the same facility where Hubble had made his original Cepheid discovery 2 decades earlier. A German-born astronomer named Walter Baade, exempted from wartime military service and working at the observatory throughout this period, took advantage of those unusually dark skies to capture the sharpest photographs of Andromeda's core taken up to that point. What he found, published in 1944, was that Andromeda actually contained 2 distinct populations of stars. One was an older, redder group concentrated in the central bulge and within globular clusters. The other was a younger, bluer group found within the spiral arms and active star-forming regions. Baade called these Population 2 and Population 1, respectively, terminology that astronomers still use today to describe stellar populations throughout the universe, not just within Andromeda. The distinction turned out to matter enormously for distance measurements as well, because Bardet realized that the Cepheid variables Hubble had originally used belonged to two subtly different types, one associated with each population, and that Hubble had unknowingly mixed the two together when calibrating his original distance calculation. Correcting for that mismatch effectively doubled the estimated distance to Andromeda overnight, one of the largest single revisions in the galaxy's measured distance. It's a clear demonstration of how a subtle, previously unrecognized detail in stellar physics could ripple outward to reshape astronomers' understanding of the entire scale of the universe. A third independent distance check came later still, using a technique called the tip of the red giant branch method. As stars like our own sun age and exhaust the hydrogen fuel in their cores, they swell into red giants, growing brighter and cooler over time, until they reach a very specific, predictable maximum brightness, at which point a sudden internal change, called the helium flash, occurs, and the star's outward appearance shifts again. That maximum brightness point turns out to be remarkably consistent across different stars, regardless of a galaxy's age or chemical composition. That makes it an extremely reliable, if less famous, standard candle, similar in spirit to Leavitt's Cepheid variables, but based on an entirely different underlying physical process. Applying this method to the enormous population of red giant stars visible within Andromeda's halo, astronomers arrived at a distance estimate closely matching the figures derived from Cepheid variables and eclipsing binaries. It was yet another independent confirmation of the same basic number, roughly 2.5 million light-years, arrived at through a completely different physical mechanism. Modern infrared observations have added a finer layer of detail to Andromeda's dust as well. Data gathered by the James Webb Space Telescope in 2023 examined the composition of that dust more closely than any previous instrument. It identified the specific chemical signatures of complex carbon-based molecules called polycyclic aromatic hydrocarbons woven throughout the galaxy's dust lanes, alongside silicate grains and small amounts of water ice, particularly within the colder, denser regions associated with active star formation. These are the same general categories of material found within dust clouds throughout our own Milky Way, the raw ingredients eventually incorporated into new stars and new planets. They're also, potentially, the basic chemical building blocks life elsewhere might eventually depend on. Finding broadly similar dust chemistry within Andromeda reinforces a point that comes up again and again throughout its study, that despite its enormous scale and its slightly different history, Andromeda is built from fundamentally the same materials, following fundamentally the same physical processes as the galaxy we call home. So now, what Andromeda actually is, because the modern numbers are almost as jarring as Hubble's discovery was in 1925. Andromeda sits at a distance of about 2.5 million light-years from Earth. Light, traveling at roughly 299,792 kilometers per second, takes 2.5 million years to cross that gap. Which means, when you look at Andromeda tonight, you are not seeing it as it is now. You are seeing light that left it 2.5 million years ago, back when our ancestors were early members of the genus Homo, walking upright on the plains of Africa, using simple stone tools. That light has been traveling this entire time, silently crossing the emptiness between galaxies, arriving in your eye at this exact moment. Whatever Andromeda looks like today, we won't know for another 2.5 million years. The physical size of Andromeda is where most people's intuition completely breaks down. Our own Milky Way is large by any everyday standard, spanning roughly 100,000 light-years across. Andromeda dwarfs it. Current measurements put its diameter at somewhere around 220,000 light-years, more than double the width of our own galaxy. To put that in terms of scale rather than comparison, imagine a disk of stars, gas, and dust so wide that light itself needs 220,000 years just to cross from one edge to the other. Not to travel around it, just to cross it in a straight line. And that disk isn't sparse. It's packed with matter, spinning slowly under the pull of its own gravity, a process that takes hundreds of millions of years to complete a single rotation. Sit with that rotation period for a moment, because it says something important about how differently galaxies experience time compared to anything on human scales. A single rotation of Andromeda's disk takes somewhere in the range of several 100 million years to complete. Since complex life first crawled onto land here on Earth, Andromeda has completed only a handful of full rotations. Since the extinction of the dinosaurs, it hasn't even managed one. Every human civilization that has ever existed, every war, every empire, every language spoken and forgotten, fits into a sliver of time so small relative to a single turn of that enormous disk that it barely registers as a fraction at all. That's not meant to diminish human history. It's meant to place it, honestly, within a frame large enough to actually contain it. This is why Andromeda appears so large in our sky, despite being millions of light-years away. Distance normally shrinks things. The farther an object is, the smaller it looks. But Andromeda is so physically enormous that even at 2.5 million light-years, its apparent size in the sky is roughly 3 degrees across, wider than 6 full moons lined up next to each other. Almost nobody sees this with their own eyes, because the outer regions of the galaxy are so faint that only long-exposure photography reveals them. What you can see with the naked eye is just the bright central core, a small, concentrated fraction of the true structure. The rest, the sweeping spiral arms, the outer disk, the faint stellar halo, extends far beyond what your eyes alone can detect, spreading quietly across a patch of sky 6 times wider than the moon you're used to seeing. Andromeda also holds a quiet distinction among astronomers. It's generally considered the most distant object you can see with nothing but your own eyes under good conditions. Everything else you can see without a telescope, every star scattered across the night sky, exists within our own galaxy, at most a few thousand light-years away. Andromeda sits roughly 1,000 times farther than that, and it's still visible. A testament to just how much light 1 trillion stars can produce, even after that light has spread and faded across 2.5 million years of empty space. Finding it yourself doesn't require expensive equipment. Under reasonably dark skies, away from the worst of urban light pollution, you can pick out that faint, elongated smudge with nothing but your own eyes, once you know where to look. It sits roughly northeast of the Great Square of Pegasus, close to the chained figure of the Andromeda constellation itself. A basic pair of binoculars improves the view considerably, revealing a distinctly oval, softly glowing shape, brighter toward the center. The 2 satellite galaxies, M32 and M110, are sometimes visible nearby too, as smaller, fainter smudges of their own on a particularly clear dark night. A small telescope reveals more structure still, hints of the dust lanes crossing the disk, a brighter, more concentrated core. though even a large amateur telescope won't resolve individual stars across most of the galaxy, since Andromeda's stars, despite there being a trillion of them, are simply too faint individually at that distance for most backyard equipment to pick out. What you're seeing through any telescope smaller than a major observatory instrument is still fundamentally the combined, blended light of enormous numbers of stars, rather than points of light representing single suns. Light pollution is the single biggest obstacle to seeing Andromeda well. Even a moderately bright suburban sky can wash out the fainter outer regions of the disk almost entirely, leaving only the brightest central core visible, a small fraction of the galaxy's true extent. It's part of why so many people underestimate Andromeda's actual size in the sky. Most people have only ever seen it, if they've seen it at all, as a small, unremarkable smudge. In truth, under a genuinely dark sky, its faint outer halo spans a region of sky roughly 6 times wider than the full moon. Most of it simply too dim to survive the glow of modern artificial lighting. Now think about what's actually inside that disk, layer by layer. Like the Milky Way, Andromeda has a distinct structure. At its center sits a dense, bright bulge of older, redder stars, tightly packed together, orbiting the galactic core in complex, overlapping paths. Surrounding that bulge is the main disk, a relatively flat, rotating plane organized into sweeping spiral arms, where most of the galaxy's stars, gas, and dust reside. Within those arms, astronomers have identified numerous regions of active star formation, glowing clouds of hydrogen gas called HII regions, where new stars are actively being born out of collapsing clouds of gas and dust. Dark, twisting lanes of dust thread through the disk as well, visible in detailed photographs as dark ribbons cutting across the brighter starlight, marking regions where dense clouds of material block the light of stars behind them. Beyond the visible disk lies something far more difficult to observe directly: a vast, extended stellar halo, a sparse, roughly spherical distribution of older stars and globular star clusters, extending far beyond the edge of the bright disk itself. Recent studies using the Hubble Space Telescope have mapped this halo out to distances of nearly 1 million light-years from Andromeda's center, describing it as an enormous, extended atmosphere of gas surrounding the galaxy, sometimes called the circumgalactic medium. That halo of diffuse material is so large that if it were visible to the naked eye, it would appear roughly 3 times the width of the constellation of the Big Dipper in our sky. It's effectively invisible in ordinary observation, though, detectable only indirectly, by measuring how it absorbs light from more distant background objects passing through it. Some estimates suggest this halo extends far enough that it may already be brushing against the outer halo of our own Milky Way, meaning, in a sense, the two galaxies have already begun to touch, long before their visible disks ever meet. That 2020 result came from a research team led by astronomer Nicholas Lehner, who used the Hubble Space Telescope not to photograph Andromeda directly, but to observe roughly 43 distant background quasars, extremely bright, extremely distant galactic cores, whose light happens to pass through Andromeda's extended halo on its way to Earth. By carefully analyzing how that background light was absorbed and altered as it passed through the otherwise invisible gas surrounding Andromeda, the team was able to map the halo's extent, density, and composition indirectly. It's the same basic principle used in gravitational microlensing searches, but applied here to trace diffuse gas rather than compact dark objects. The results showed the halo, extending in a roughly spherical shape out to nearly 1,300,000 light-years in some directions, with a denser, more compact shell closer to the galaxy itself. The results also hinted that similar invisible halos likely surround most large galaxies throughout the universe, an enormous reservoir of gas several times the mass of the visible galaxy itself. It had simply gone undetected before, because there had never been enough sufficiently bright background objects and precise enough instruments to reveal it. Andromeda also hosts an extensive population of globular clusters, tightly bound, spherical groupings of old stars that orbit the galaxy's core. The Milky Way has roughly 150 known globular clusters. Andromeda has far more, with current catalogues listing somewhere around 460, some of the oldest and most massive star clusters known in the entire local group of galaxies. One of them, known simply by its catalogue designation, Mayol 2, also called Globular 1, is the most luminous globular cluster known anywhere in the local group, containing several million stars packed into a region only around 100 light-years across. And it may in fact be the stripped-down remnant core of a much smaller galaxy that Andromeda consumed at some point in its long history. That's not an isolated idea either. Andromeda's history is one of repeated mergers and consumption of smaller galaxies, a pattern common to large galaxies throughout the universe. In 2001, astronomers discovered something that made this history impossible to ignore: a giant stream of stars extending outward from Andromeda's disk, curving across an enormous span of space. It was visible in deep photographic surveys as a faint river of light separate from the main body of the galaxy. This structure, now called the giant stellar stream, is understood to be the torn-apart remains of a smaller galaxy that Andromeda pulled apart and absorbed, its stars stretched into a long tidal tail by the immense gravitational forces involved. It's much like the tidal tails predicted for the future Milky Way collision, just already completed, on a smaller scale, sometime in the relatively recent astronomical past. Studies of this stream suggest the disrupted galaxy was consumed somewhere between 100 million and a few billion years ago, and its shattered remains are still slowly settling into Andromeda's outer halo, a visible scar from an earlier collision. Andromeda's compact companion galaxy, M32, may itself be connected to this same violent history. Some researchers propose that M32 was once a much larger spiral galaxy, one that had its outer disk and gas almost entirely stripped away during a close, high-speed encounter with Andromeda. What's left behind is only its small, dense, compact core, the object we see today. If that theory holds, M32 represents something rare, a galaxy that has already survived. In a sense, the very kind of violent gravitational encounter that Andromeda and the Milky Way are now heading toward. For a long time, astronomers assumed that with a star count that high and a galaxy that massive, Andromeda's actual mass would dwarf the Milky Way's as well. That assumption has been revised. More recent studies, factoring in the distribution of dark matter, the invisible material that makes up most of a galaxy's gravitational mass, suggest that the two galaxies may actually be much closer in total mass than previously believed. Some estimates now put the Milky Way's total mass, dark matter included, at roughly comparable levels to Andromeda's, even though Andromeda has more visible stars. This was a genuine surprise in galactic astronomy. For decades, Andromeda was treated as the undisputed heavyweight of our local group of galaxies, the dominant member that the Milky Way orbited around in some indirect sense. The newer data complicates that picture, suggesting a more balanced relationship between two roughly equal giants, rather than a large galaxy and a smaller one. The debate over the precise mass ratio is still active, and it depends heavily on how much dark matter each galaxy actually holds, something that can only be inferred indirectly through its gravitational effects on visible matter. One of the classic methods used to estimate the combined mass of the Andromeda and Milky Way system relies on something astronomers call the timing argument, an approach first worked out in the 1950s. The logic behind it is fairly elegant. Both galaxies are presumed to have formed relatively close together, near the beginning of the universe's history, and then drifted apart under the influence of the early universe's overall expansion. Eventually, they slowed down, stopped, and began falling back together again under their mutual gravity, the approach we're now able to measure directly. By working backward from Andromeda's current distance, its current approach velocity, and the total age of the universe, astronomers can calculate how much combined mass would be required to produce exactly that pattern of separation and return. The answer that calculation produces is enormous, several trillion times the mass of the Sun, when both galaxies and their surrounding dark matter halos are included. That figure is broadly consistent with, though not identical to, estimates derived from rotation curves and satellite galaxy motions. Having multiple independent methods, the timing argument, rotation curve measurements, and satellite dynamics, all converging on roughly similar answers, gives astronomers reasonable confidence in the overall scale of mass involved. The precise details and the exact split between Andromeda and the Milky Way individually remain an active area of refinement. The eventual merger won't just involve the two central galaxies either. Every satellite galaxy currently orbiting Andromeda or the Milky Way, dozens of smaller companions on both sides, will be caught up in the same long process, their orbits perturbed and reshaped by the changing gravitational landscape as the two much larger galaxies swing past each other and eventually combine. Some satellites may be flung outward onto much wider, looser orbits around the newly formed Milkdromeda. Others may be pulled inward and eventually consumed entirely, absorbed the same way Andromeda has already absorbed smaller galaxies in its own past, adding their stars to the growing halo of the merged system. The Triangulum Galaxy, M33, that third large member of the local group, possibly already gravitationally bound to Andromeda, faces its own uncertain path through all of this. Some simulations suggest it could be flung onto a wide, independent orbit around the merged Milkdromeda system, continuing on largely undisturbed as a satellite of the new, combined galaxy. Others suggest a more direct interaction is possible, given its already close relationship with Andromeda, potentially leading to its own eventual merger with the larger system, on a timescale even longer and even less certain than the primary Andromeda and Milky Way collision itself. Either way, the entire architecture of the local group, not just the two dominant galaxies at its center, is set to be reshaped by this process, a slow, billion-year reorganization of nearly everything gravitationally tied to our part of the universe. Andromeda contains an estimated 1 trillion stars. Compare that to the Milky Way, which contains somewhere between 100 billion and 400 billion stars, depending on the estimation method used. Even at the high end of that range, Andromeda still contains roughly 2.5 to 10 times as many stars as our own galaxy. 1 trillion is a number that's almost impossible to hold in your head in any meaningful way. If you tried to count to 1 trillion, one number every second, without stopping to sleep or eat, it would take you over 31,000 years. And each one of those numbers in Andromeda's case represents an actual star, many of them with their own planets, their own solar systems, their own quiet corners of space entirely unknown to us. All of that starlight adds up to an enormous total output of energy. Astronomers measure a galaxy's overall brightness using a scale called absolute magnitude, where lower, more negative numbers indicate greater intrinsic brightness. Andromeda's absolute magnitude works out to roughly -21, making it intrinsically brighter than the Milky Way by a meaningful margin, consistent with its larger population of stars, even accounting for the uncertainty in exactly how their total masses compare once dark matter is included. If you could somehow place Andromeda at the same distance as our nearest stellar neighbor, a truly nonsensical scenario given the physical size involved, it would outshine every star in the night sky, combined many times over. A single, overwhelming source of light dominating the entire sky. Of course, spread out across 220,000 light-years and viewed from 2.5 million light-years away, all of that light dilutes down into the faint, unremarkable smudge most people glimpse only briefly, if they notice it at all. That gap between the staggering total energy output of 1 trillion stars and the faint, easily overlooked smudge it actually appears as from Earth, is itself a useful way to understand just how vast the distances involved really are, since it takes genuinely enormous amounts of intervening space to dim something that bright down to something so easy to miss. Andromeda isn't alone out there either. Just like the Milky Way, it has its own system of satellite galaxies, smaller companions caught in its gravitational pull, orbiting it the way moons orbit a planet. The two largest and most easily observed are M32 and M110, both visible in amateur telescopes on a clear night alongside Andromeda itself. M32 is a compact, dense little galaxy, thought to have once been much larger before a close encounter with Andromeda stripped away much of its outer material. It's classified as a compact elliptical galaxy, a rare type, containing a surprisingly dense concentration of stars, likely numbering in the billions, all packed into a sphere only around 6,000 light-years across. It's small enough that some astronomers describe it as almost pathological, a galaxy that shouldn't exist in its current form based on how galaxies normally evolve. That is exactly why the theory that it was once far larger and stripped down by Andromeda's gravity has gained so much support. M110 is more diffuse, an elliptical galaxy with a faint, spread-out glow, roughly 15,000 light-years across. Unlike most elliptical galaxies, which typically contain old stars and little to no gas or ongoing star formation, M110 shows faint traces of dust lanes and a small amount of recent star formation, an unusual feature for its type. This suggests it may have absorbed gas from a smaller companion of its own at some point in the past, or that Andromeda's gravity has been slowly feeding it material. Beyond these two, astronomers have identified dozens of fainter dwarf satellite galaxies surrounding Andromeda, catalogued simply as Andromeda 1 through roughly 30, along with older designations like NGC 147 and NGC 185. Some of these contain only a few million stars, barely more than oversized star clusters in the grand scheme of things. NGC 147 and NGC 185 orbit as a pair, both dwarf spheroidal galaxies, both faint and diffuse. located farther out from Andromeda's core than M32 or M110. Both are thought to be on long, slow orbital paths that will eventually bring them closer in, where the same tidal forces that reshaped M32 could begin reshaping them as well. The largest of the fainter dwarf companions, simply named Andromeda 2, spans a modest few thousand light-years and contains a stellar population dominated by old, faint stars. A fairly typical example of the kind of small, ancient galaxy that large spirals like Andromeda tend to accumulate in great numbers over cosmic time. These satellites arrange themselves in surprising ways. Some studies have found that a significant number of Andromeda's satellite galaxies orbit in a thin, coordinated plane, almost like a disk of their own, rather than scattering randomly in every direction the way basic gravitational models would predict. Why that happens is still being studied. It might reflect how these satellites formed, or it could be evidence of larger structures in the cosmic web guiding their alignment. Either way, it's a reminder that even a system as well studied as Andromeda still holds open questions. Andromeda has also given astronomers a direct look at some of the most violent individual events a galaxy can produce. In 1885, a bright new point of light appeared within Andromeda itself, visible even in modest telescopes of the era, and briefly bright enough that some observers worried it might be a nearby object rather than something inside a distant nebula. It was later recognized as a supernova, the catastrophic explosion marking the end of a massive star's life, and it remains the only supernova ever observed within Andromeda from Earth. Astronomers at the time didn't understand what they were looking at. They had no concept of Andromeda as a separate galaxy yet, since that wouldn't be established for another 40 years. So the sudden appearance of this new light source was simply catalogued as a nova, a designation for a much smaller, non-destructive stellar outburst, and given the name S. Andromedae. It took decades of hindsight and the eventual understanding of what Andromeda actually was for astronomers to realize what they'd witnessed in 1885. It was, in fact, one of the most energetic events in the universe, a single star's final collapse, visible faintly to the naked eye across 2.5 million light-years of empty space. That kind of event is rare. On average, a galaxy like Andromeda might produce only a handful of supernovae per century. So witnessing one, even faintly, was an extraordinary stroke of observational luck. Smaller stellar outbursts, ordinary novae rather than full supernovae, are far more common. And Andromeda produces dozens of them every year, faint temporary brightenings scattered across its disk as certain types of binary star systems periodically flare. Within Andromeda's disk, one particular star-forming region stands out enough that it has its own catalogue designation, NGC 206. It's an enormous cloud of gas and young hot stars, roughly 4,000 light-years across, making it one of the largest star-forming complexes known in the entire local group of galaxies, larger than any comparable region found within our own Milky Way. Regions like this are where Andromeda's ongoing, if modest, star formation is concentrated. Dense pockets of raw material collapsing under gravity to form new generations of stars. Some of those stars will eventually end their lives as supernovae themselves, enriching the surrounding gas with heavier elements that future generations of stars and potentially future generations of planets will eventually be built from. Andromeda and the Milky Way aren't the only large members of our cosmic neighborhood. Together, they anchor what astronomers call the local group, a gravitationally bound collection of roughly 80 known galaxies, spanning a region of space about 10 million light-years across. The third largest member of this group is the Triangulum Galaxy, catalogued as M33, a smaller, spiral galaxy located close to Andromeda in the sky and possibly bound to it gravitationally as a satellite in its own right. Astronomers have detected a faint bridge of hydrogen gas stretching between Andromeda and Triangulum, suggesting the two may have interacted directly at some point in the past. Or they may be in the early stages of a slow gravitational dance that could eventually end in another merger. Long after the larger Andromeda and Milky Way collision has already reshaped the neighborhood. Every other member of the local group, dozens of dwarf galaxies scattered across that 10 million light-year span, is comparatively tiny, some containing only a few thousand or a few million stars. Andromeda and the Milky Way are the two dominant giants, and virtually everything else in our cosmic neighborhood exists within their combined gravitational influence in one way or another. Zoom out even further, and the local group itself is just a small piece of something much larger. Our local group belongs to a broader collection of galaxy groups and clusters called the Virgo supercluster, centered on the much larger and more crowded Virgo cluster, itself containing well over 1,000 galaxies, located roughly 54 million light-years away. And the Virgo supercluster, in turn, is just one lobe of an even larger structure, a vast, sprawling supercluster complex named Laniakea, a Hawaiian word meaning immense heaven. It was identified in 2014 through a careful mapping of how galaxies across hundreds of millions of light-years are all being gravitationally pulled toward a common region of especially dense matter. Laniakea spans roughly 500 million light-years and contains the mass of about 100,000 galaxies, the size of the Milky Way. Every galaxy within it, including our own, including Andromeda, is slowly flowing along invisible gravitational contours toward that distant, dense concentration of mass. It's the way water flows downhill along a landscape, except here, the landscape is made of gravity itself, shaped by the combined pull of everything within reach. It's a useful reminder of scale within scale. Andromeda feels enormous when you're trying to picture 220,000 light-years, or 1 trillion stars. But it's a single member of a local group that's itself a minor gathering within a supercluster spanning 500 million light-years, which is itself just one structure among countless others scattered across the observable universe. Every layer you zoom out to reveals another layer of structure, another scale that makes the previous one look small by comparison, and it never quite stops. There's some fitting symmetry in the name Andromeda itself. In Greek mythology, Andromeda was a princess, chained to a rock as an offering to a sea monster, and eventually rescued by the hero Perseus. The constellation carries that name because early stargazers, tracing patterns among the fixed points of light overhead, saw in that region of sky a chained figure. She was surrounded by the neighboring constellations of her parents, Cepheus and Cassiopeia, and her rescuer, Perseus. Together, they form an entire mythological scene mapped across the northern sky. Nobody involved in naming that constellation thousands of years ago had any way of knowing that tucked within it was a smudge of light containing more individual stars than there are grains of sand on every beach on Earth combined. The name stuck long after the mythology faded into cultural memory, carried forward simply because that's where in the sky you look to find it. Andromeda played a direct role in one of the most important discoveries in modern astrophysics, one that has nothing to do with stars you can actually see. In the 1970s, an American astronomer named Vera Rubin, working alongside Kent Ford, carefully measured how fast stars and gas were orbiting at different distances from Andromeda's center. Under ordinary expectations, based purely on the visible matter concentrated toward the galaxy's core, stars, far out on the edges of the disk, should orbit noticeably slower than stars closer in, the same way planets farther from the Sun in our own solar system move slower than planets closer to it. That's not what Rubin and Ford found. Instead, the orbital speed stayed roughly flat, remaining just as fast far out on Andromeda's edges as they were closer to its center. A result that made no sense if the only matter present was the matter astronomers could actually see through a telescope. The only way to explain those flat rotation speeds was to assume Andromeda, and by extension galaxies in general, contained a much larger amount of unseen mass, extending in a roughly spherical halo far beyond the visible disk, exerting gravitational pull without emitting or reflecting any detectable light. Rubin's measurements of Andromeda, followed by similar results in dozens of other galaxies, became some of the strongest early evidence for what we now call dark matter. A form of matter that doesn't interact with light at all, yet appears to make up roughly 85% of all the matter in the universe. To this day, nobody knows exactly what dark matter actually is, only that its gravitational fingerprints are unmistakable. And Andromeda, sitting close enough for its rotation to be measured star by star, was one of the objects that first revealed it. At the very center of Andromeda, deep within its dense stellar core, sits a supermassive black hole. Its presence was first inferred in the late 1980s through careful measurement of how stars near Andromeda's center were moving, orbiting far too quickly to be explained by visible matter alone. An astronomer named John Cormendy led some of the earliest work on this in 1988, measuring the velocities of stars near Andromeda's nucleus. He found they moved so rapidly that an enormous, unseen concentration of mass had to be present to hold them in orbit gravitationally. A compact dark object, rather than any ordinary distribution of visible stars. That early evidence was later confirmed and refined, using the Hubble Space Telescope, launched into orbit not long afterward, which measured the motion of stars deep within the core with enough precision to calculate the mass of the object they were orbiting. It was that same set of Hubble observations, led by astronomer Todd Lauer in the early 1990s, that first revealed the strange double nucleus structure at Andromeda's very center, a discovery that initially puzzled researchers. Two distinct bright points, so close to a single black hole, seemed to defy simple explanation, until later modeling showed how an elongated, eccentric disk of orbiting stars could produce exactly that kind of illusion. It's catalogued simply by its position, and it carries an estimated mass of somewhere between 100 million and 230 million times the mass of our own Sun. For comparison, the supermassive black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million times that of the Sun, which means Andromeda's central black hole could be tens of times more massive than our own galaxy's central monster. That's an enormous amount of mass, concentrated into a single point, a region of space where gravity has overwhelmed every other force, warping the fabric of space-time itself so severely that nothing, not even light, can escape once it crosses the boundary known as the event horizon. Stars near Andromeda's core orbit this black hole in ways that reveal its presence indirectly, moving at speeds and along paths that can only be explained by an object with that much concentrated mass. The stellar population immediately surrounding it is unusual too. Rather than a simple, smooth core, observations from the Hubble Space Telescope revealed a strange double nucleus structure near Andromeda's center. Two distinct concentrations of stars close together. Astronomers now believe this is actually the result of an eccentric disk of older stars orbiting the black hole in an elongated pattern, creating the illusion of two separate cores, when in fact it's one warped structure. Now here's the part of this story that turns Andromeda from a distant curiosity into something far more personal. Andromeda is not standing still. It's moving toward us, and it has been for a very long time. Using precise measurements of how the galaxy's light shifts, building on that original observation Vesto Slipher made over a century ago, astronomers determined that Andromeda is approaching the Milky Way at a speed of roughly 110 kilometers per second. That's about 396,000 kilometers every hour, closing the gap between our two galaxies a little more with each passing moment. For most of the time since this approach velocity was first measured, scientists weren't entirely sure whether Andromeda would actually collide with the Milky Way, or simply pass by at a distance, pulled into a wide, sweeping orbit without ever truly merging. The uncertainty came down to sideways motion, the component of Andromeda's movement across our line of sight, which is far harder to measure than motion directly toward or away from us. It took data from the Hubble Space Telescope, gathered over a 5 to 7 year period, specifically to track that motion, to finally pin the sideways component down with enough precision to model the future collision with confidence. The conclusion, published in 2012 by astronomer Roland van der Merel and colleagues, and later reinforced by additional measurements from the Gaia Space Telescope over the following decade, was clear. Andromeda and the Milky Way are on a collision course. Not a near miss. Not a distant flyby. An actual merger, projected to begin in roughly 4 billion years. It's worth noting that this picture, confident as it sounds, has actually grown a bit more nuanced in the past couple of years. A study published in 2025, led by astronomer Til Sawala, revisited the merger calculation while incorporating the gravitational influence of additional local group members that earlier models had left out, particularly the Large Magellanic Cloud, a substantial satellite galaxy of our own Milky Way. The team also worked from a slightly updated estimate of Andromeda's own satellite masses. Adding those additional gravitational tugs into the simulation introduced enough extra uncertainty that the study's authors calculated only about a 50% chance of a direct collision within the coaling. Next 10 billion years. That's a far cry from treating the merger as an essentially guaranteed near-term certainty, the way earlier models, based on a simpler two-galaxy system, had suggested. That doesn't overturn the broader picture. Andromeda is still approaching. A merger, sooner or later, remains the most likely long-term outcome, given the two galaxies' mutual gravity and their relatively close distance within the local group. But the exact timing, and even the exact outcome, close call or full collision, remains an active area of research. It gets refined as each new generation of data comes in, additional satellite galaxies factored in, more precise motion measurements, sharpening the underlying simulation just a little further. The same way our understanding of Andromeda's basic distance was refined repeatedly across the 20th century before settling on today's figures. Andromeda's presence in the night sky has left a mark on human culture that stretches well beyond scientific catalogues and research papers. Its mythological name, inherited from a constellation, has itself become shorthand across science fiction for the idea of something vast, distant, and other. It's a galaxy invoked in countless novels, films, and games. It works as a symbol of the outer edge of what's conceivable, a destination just barely within reach of imagination, even when it's nowhere close to being within reach of actual technology. That cultural weight isn't entirely undeserved. Long before anyone understood what Andromeda actually was, it already carried a kind of quiet mystery, a smudge of light that refused to resolve into anything familiar, no matter how carefully early observers studied it. In a strange way, the scientific reality turned out to be even more remarkable than the fiction it later inspired. It's not a metaphor for distance or mystery, but an actual trillion-star structure, close enough to study star by star, and, eventually, destined to become part of the same galaxy we call home. It's worth pausing here to understand what a galactic collision actually looks like, because it's nothing like two solid objects smashing together. Galaxies are, in a very real sense, mostly empty space. The average distance between stars within a galaxy, like the Milky Way or Andromeda, is measured in light years, and even in the densest regions, stars are separated by distances that dwarf the stars themselves many times over. Because of that spacing, when two galaxies collide, the chance of any two individual stars actually striking each other is almost zero. Our own Sun, for example, has an extremely low probability of ever physically encountering another star during the entire merger process. What collides instead is the overall structure, the gravitational shape of each galaxy, the vast clouds of gas and dust, and the general distribution of stars, all of which will be pulled, stretched, and reshaped by the immense combined gravity of both systems. Spiral arms will be torn apart. Long streams of stars will be flung outward into intergalactic space, forming what astronomers call tidal tails, some of which may stretch for hundreds of thousands of light years, not unlike the giant stellar stream already trailing from Andromeda today, the visible scar of its last such encounter. The two galactic disks will pass through each other, loop back under mutual gravity, and pass through again, in a slow, repeated dance that could take hundreds of millions of years to fully play out. Picture, for a moment, what that first pass might actually look like from somewhere within the Milky Way, assuming a planet and something capable of observing still existed there 4 billion years from now. Andromeda wouldn't arrive suddenly. It would have been growing steadily larger in the sky for millions of years already, its disk gradually filling more and more of the darkness, its faint spiral arms becoming visible without a telescope, long before any actual collision began. As the two galaxies made their first close approach, the sky itself would begin to change shape. Familiar constellations distorted as foreground stars from our own galaxy's disk-shifted position relative to the enormous, sprawling structure of Andromeda, now filling a huge portion of the sky behind them. Bright new star-forming regions would flare up where the two galaxies' gas clouds first collided and compressed. Brief points of intense blue-white light scattered unevenly across the merging structure, regions that would fade again over a few million years as their fuel was exhausted. There would be no single dramatic night when everything changed. Instead, over the course of millions of years, generation after generation, the sky would simply keep transforming, slowly, continuously. Eventually, the familiar spiral shapes of both galaxies would give way entirely to something new. That kind of scale, change measured across millions of years, rather than a single lifetime, is genuinely difficult for a human mind to hold on to, since virtually nothing in ordinary human experience unfolds anywhere close to that, slowly. But it's exactly the kind of timescale galaxies operate on, patient beyond any human comparison, indifferent to anything as brief as a single generation, or a single civilization, or a single species. Simulations of this merger, run by teams of astrophysicists using supercomputers, suggest that the process won't be a single dramatic event. Instead, it will be a long, gradual transformation spanning billions of years. One of the most detailed simulations, first circulated in 2007 and formally published in 2008 by astronomers T.J. Cox and Abraham Loeb, modeled the entire encounter step by step, and later work using precise Hubble Space Telescope measurements of Andromeda's sideways motion, led by astronomer Roland van der Merel and colleagues, refined the timeline even further. Together, these studies paint a fairly consistent picture of how the next several billion years will unfold. Around 2 billion years from now, Andromeda would already be dramatically larger and brighter in the night sky than it appears today, though still recognizably a separate, distant galaxy. Its disk would already be starting to show the faint effects of the Milky Way's gravitational pull stretching its outer edge. By roughly 3,750 million years from now, the two galaxies would be close enough that their outer halos and extended gas clouds begin to visibly interact, tidal forces starting to distort the shape of both galaxies, faint streams of stars beginning to bridge the gap between them. The first close pass is projected to happen around 4 billion years from now. At that point, the two galaxies won't fully merge immediately. They'll interact, distort each other's shapes, and then drift apart again, still bound by gravity, before swinging back for another pass, perhaps around 1 billion years after the first encounter. During that first pass, simulations suggest the sky, if anyone were watching from a surviving world within either galaxy, would show Andromeda's disk stretched into a long, glowing arc. It would no longer be a neat spiral, but a smeared, elongated structure torn by the gravitational tug-of-war between the two systems. Over the following 2 billion years or so, through repeated passes, the two galaxies will gradually lose their distinct spiral structures and merge into a single, much larger galaxy, with the process largely complete somewhere around 6 to 7 billion years from now. Astronomers have given this hypothetical future galaxy an informal name, combining the two originals into one word: Milkdromeda. The final result is expected to be a giant elliptical galaxy, lacking the tidy spiral arms either galaxy has now, its stars redistributed into a more rounded, less structured shape. The common outcome when two large spiral galaxies merge. During the more violent stages of the merger, the enormous clouds of gas within both galaxies are expected to collide and compress, triggering a significant burst of new star formation. This starburst phase could briefly make the merging galaxies far brighter than either one is today. Before that available gas is used up and star formation gradually slows, eventually leaving behind a quieter, aging elliptical galaxy with very little fuel left for new stars. Even the two central supermassive black holes are expected to eventually spiral toward each other over these billions of years and merge as well. That event would release a burst of gravitational waves, ripples in space-time itself, powerful enough to be detected, in principle, from across much of the observable universe, if there happened to be anyone around with the instruments to look for it. Some simulations suggest that before the two black holes fully merge, they could orbit each other as a tight binary pair for tens of millions of years, occasionally flaring brightly as gas and disrupted stars fall inward. It would be a slow, drawn-out prelude to the final collision of two objects, each individually more massive than millions of suns combined. What happens to our own solar system during all of this is one of the most common questions people ask, and the honest answer is probably not very much. At least, not directly from the collision itself. Because stars are spaced so far apart, our Sun and its planets are extremely unlikely to be involved in any direct stellar collision during the merger. What is far more likely is that our solar system gets gravitationally nudged, shifted to a different position within the newly forming galaxy, perhaps flung farther out into a looser orbit around the combined galactic center, or pulled into a different orbital path entirely. The night sky, for any hypothetical observer around at the time, would look completely different. During the early stages of the collision, before the two galaxies fully merge, the sky would show Andromeda growing larger and larger over millions of years, eventually filling a significant portion of the visible sky, its light mixing with the light of our own galaxy's stars in ways no human has ever witnessed. It's worth noting that this timeline, 4 billion years for the initial approach, several billion more for the full merger, is so far in the future that it's largely academic for humanity in any near-term sense. Our Sun is expected to exhaust its hydrogen fuel and expand into a red giant in roughly 5 billion years. A transformation that will make Earth uninhabitable long before the Andromeda merger reaches its later stages. Whatever life, if any, exists on Earth or has expanded beyond it, by that point we'll be dealing with challenges far more immediate than a slow-motion galactic collision playing out over cosmic timescales. Stepping back from the collision and looking at Andromeda as it exists right now in its current unmerged state, it remains one of the most studied objects in the sky. That's precisely because it's close enough, in cosmic terms, to actually resolve individual stars and structures within it, something that's far harder to do with more distant galaxies. The Hubble Space Telescope has produced some of the most detailed images ever taken of another galaxy by observing Andromeda, a mosaic assembled from hundreds of individual exposures, revealing over 100 million individual stars and thousands of star clusters across a portion of the galaxy's disk. That image alone represents years of observation time and remains one of the largest and most detailed photographs ever produced of any astronomical object. A separate long-term survey, known as the Panchromatic Hubble Andromeda Treasury, or PHAT for short, spent years methodically imaging roughly a third of Andromeda's disk across multiple wavelengths of light, cataloging well over 100 million stars individually and mapping star formation history across the galaxy in unprecedented detail. More recently, the James Webb Space Telescope has turned its infrared instruments toward Andromeda as well, cutting through dust that would otherwise obscure regions of active star formation, revealing details about the galaxy's structure that visible light observations simply cannot capture. Every new generation of telescope brings a sharper, more detailed picture of this galaxy, refining our understanding of its mass, its satellite system, its rate of star formation, and the precise dynamics of its eventual collision course with our own. Visible light is only part of the picture. Observing Andromeda across other wavelengths has revealed structures completely invisible to the human eye. In 2005, the Spitzer Space Telescope, observing in infrared light, revealed something unexpected hiding within Andromeda's dust. Rather than a smooth spiral pattern, the infrared image showed a distinct, glowing ring of dust and star formation, off-center from the galaxy's nucleus, giving Andromeda's structure an appearance some astronomers compared to a giant eye, with the ring forming an iris around a core that wasn't quite centered within it. The leading explanation is that this ring was created by a direct collision with a smaller companion galaxy, quite possibly the same progenitor that became the compact galaxy M32 sometime in the past few 100 million years. It was a collision energetic enough to compress gas and dust into an expanding ring, triggering waves of new star formation as it spread outward, similar in principle to the ripples that spread outward after a stone is dropped into still water. Ultraviolet observations taken by NASA's Galax satellite added further detail, highlighting the hottest, youngest, most massive stars scattered throughout Andromeda's disk. They traced out the spiral structure in a way that emphasized ongoing star formation, rather than the older, redder stellar population that dominates visible light images. X-ray observations, taken by the Chandra X-ray Observatory, revealed a different kind of activity entirely. Faint but detectable X-ray emission coming from the very center of the galaxy, consistent with a small amount of hot, superheated gas slowly spiraling into the supermassive black hole at Andromeda's core. Unlike some galaxies with extremely active central black holes, feeding on large amounts of surrounding gas and producing enormous amounts of radiation, Andromeda's central black hole appears to be in a relatively quiet, low-activity state, consuming material only slowly. That is part of why it took indirect stellar motion measurements, rather than direct observation of a bright, actively feeding black hole, to confirm it was there at all. Put all of these observations together, visible light, infrared, ultraviolet, and X-ray, and you get a far richer picture than any single image could provide. A galaxy with a disturbed, off-center dust ring from an ancient collision, active pockets of young star formation, and a vast unseen halo of dark matter. At the center of it all sits a quiet, slowly feeding black hole, anchoring the whole structure. It's also worth addressing something that surprises a lot of people, which is just how ordinary Andromeda actually is, in the sense that it's not some exceptional, rare type of object. It's a barred spiral galaxy, similar in overall classification to our own Milky Way, meaning it has a central elongated bar structure of stars, with spiral arms extending outward from it. Spiral galaxies like these are extremely common throughout the observable universe, making up a large fraction of the galaxy's astronomers' catalogue. What makes Andromeda special isn't its type. It's its proximity. Out of the billions upon billions of galaxies scattered across the observable universe, Andromeda happens to be one of the closest large galaxies to our own. It's close enough that we can study its individual stars, its satellite system, its black hole, and its structure in a level of detail that's simply impossible for galaxies millions of times farther away. It functions almost like a laboratory, a nearby example that helps astronomers understand galaxies in general, including our own. Since studying the Milky Way from the inside comes with its own set of challenges that Andromeda, viewed from the outside, doesn't share. Star formation within Andromeda has actually slowed considerably compared to its estimated past. Current measurements suggest it's forming new stars at a rate of roughly 1 solar mass worth of material per year, a relatively modest pace compared to some other spiral galaxies of similar size, and considerably slower than the rate astronomers believe it sustained several billion years ago, when repeated mergers with smaller galaxies would have compressed and stirred its gas reservoirs far more actively. The Milky Way, by contrast, still forms new stars at a somewhat higher rate. That is part of why some researchers describe our own galaxy as comparatively young and active, even sitting next to a giant like Andromeda that, in a sense, has already settled into a quieter, more mature phase of its life. There's more hiding inside that globular cluster mentioned earlier. Male 2, the enormous, densely packed cluster that may be the stripped core of a long-consumed dwarf galaxy. Observations taken in the early 2000s, using both the Hubble Space Telescope and ground-based observatories, found evidence of a compact, massive object at its center, one too heavy and too concentrated to be explained by ordinary stars alone. The leading interpretation is that Male 2 harbors what astronomers call an intermediate mass black hole, a category that sits between the relatively modest black holes formed from individual collapsed stars, typically a few times the mass of the Sun, and the supermassive black holes found at the centers of entire galaxies, which can be millions or billions of times the Sun's mass. Estimates for Male 2's central object put it at somewhere around 20,000 times the mass of the Sun, a size that fits neither category comfortably. And objects like this remain rare and difficult to confirm, since they're too small to easily detect through the same stellar orbit methods used for galaxy-scale black holes, yet too large to have formed the way ordinary stellar black holes do. If confirmed, it would support the idea that Male 2 isn't simply an oversized star cluster. It would be the surviving skeleton of an entire small galaxy that Andromeda tore apart and absorbed long ago, its outer stars stripped away, its gas gone, leaving only this dense, black hole-anchored core drifting in orbit around its much larger captor. It's worth taking a moment to sit with just how far away 2.5 million light-years actually is, in terms our current technology can relate to. The fastest object humanity has ever launched, the Parker Solar Probe, has reached speeds of over 600,000 kilometers per hour during its close passes by the Sun, faster than anything else built by human hands. Even at that extraordinary speed, sustained continuously in a straight line, which isn't actually how the probe travels, reaching Andromeda would still take somewhere in the range of 4.5 billion years. Longer than the current age of the Earth itself. Voyager 1, humanity's most distant spacecraft, launched in 1977 and now traveling beyond the edge of our solar system, moves at a comparatively modest 61,000 kilometers per hour. At that pace, reaching Andromeda would take roughly 45 billion years, several times longer than the current age of the entire universe. Even light itself, the fastest thing that exists, needs 2.5 million years to make the crossing. There is, quite simply, no meaningful sense in which Andromeda is reachable with anything resembling current or near-future technology. Its true significance isn't as a destination. It's as a mirror, a nearby example close enough to study in detail that helps us understand the kind of galaxy we ourselves live inside. Andromeda has even played a role in the search for dark matter itself, beyond Vera Rubin's original rotation curve measurements. In the 1990s, researchers used a clever technique called pixel lensing to search Andromeda's disk for evidence of a specific dark matter candidate, massive, compact objects like failed stars or ancient black holes, drifting unseen through the galaxy's halo. The idea relied on gravitational microlensing, a phenomenon predicted by general relativity, in which a massive object passing directly in front of a background star, from our point of view, briefly bends and magnifies that star's light. This causes a short, symmetric brightening before fading back to normal. Because individual stars within Andromeda's disk can't be resolved separately by ground-based telescopes, researchers instead monitored the combined brightness of small patches or pixels, of the galaxy's image over time, watching for the extremely rare, brief flickers such a lensing event would produce. Surveys conducted throughout the 1990s and early 2000s did detect a handful of candidate microlensing events within Andromeda, but not nearly enough to account for the total amount of dark matter inferred from rotation curve measurements. The conclusion drawn from this work was significant in its own right, a reasonably strong piece of evidence ruling out ordinary massive compact objects as the primary explanation for dark matter. It pointed instead toward more exotic possibilities, some new, undiscovered type of particle, rather than simply large amounts of unseen ordinary matter hiding in the dark. It's a good example of how a single nearby galaxy, studied carefully enough, can help settle major questions about the fundamental nature of the universe. Andromeda's disk itself isn't perfectly flat either. Detailed imaging has revealed that it's warped, curving gently upward on one side and downward on the other, rather than lying in a single flat plane, the way a simplified diagram might suggest. Warps like this are common in spiral galaxies, and they're generally understood to be caused by gravitational interactions, either with satellite galaxies tugging on the outer disk over long periods of time, or with the surrounding intergalactic gas the disk is slowly plowing through as it moves. In Andromeda's case, the combination of its many satellite galaxies, its history of past mergers, and its motion through the diffuse gas of the local group likely all play some role in maintaining that gentle warp. It's a reminder that even a structure as large and seemingly stable as an entire galactic disk is still being shaped by forces acting on it continuously, over timescales of hundreds of millions of years. The disk's vertical thickness adds another layer to this picture. While Andromeda's disk spans roughly 220,000 light-years across, it's remarkably thin relative to that width, with the main stellar disk measuring only around 1,000 light-years from top to bottom in its thinnest regions, thickening somewhat within the crowded central bulge. That kind of proportion, a structure 200 times wider than it is tall, is common among spiral galaxies. And it's a direct consequence of how these disks form in the first place, with rotating clouds of gas flattening under their own gravity into thin, pancake-like structures long before individual stars ever condense out of them. Older stellar populations tend to occupy a slightly thicker, more puffed-up layer within the disk, sometimes described separately as a thick disk component, while younger stars, gas, and active star-forming regions remain confined to a noticeably thinner layer closer to the galactic midplane. That's a subtle stratification, and it itself carries information about Andromeda's long formation history and about how earlier gravitational disturbances, including past mergers, have gradually puffed up and reshaped different generations of stars within the disk over billions of years. Individual stars within that disk orbit the galactic center at speeds that stay remarkably consistent across a wide range of distances, a direct consequence of the dark matter halo Vera Rubin's measurements first revealed. A star orbiting at a distance from Andromeda's center, roughly comparable to our own sun's distance from the Milky Way's center, would move at somewhere around 250 kilometers per second. It would complete a single full orbit in something on the order of 250 million years, a figure remarkably close to the orbital period of our own sun around the center of the Milky Way. That similarity isn't a coincidence so much as a reflection of how comparable the two galaxies actually are in overall structure, gravitational scale, and rotational behavior. Both are large, mature spiral systems, shaped by billions of years of broadly similar physical processes. now slowly converging toward a shared future, neither one experienced alone for most of its history. None of this violent history is unusual, and it's worth being clear about that, because it can be tempting to think of Andromeda's collisions and consumed companions as somehow exceptional. Our own Milky Way has a similarly violent past, one that astronomers only fully pieced together fairly recently. Detailed data from the Gaia Space Telescope, released starting in 2018, revealed clear evidence within the motion and chemical composition of nearby stars that the Milky Way itself absorbed a substantial dwarf galaxy sometime between 8 and 11 billion years ago. That event is now commonly called the Gaia-Enceladus merger, sometimes nicknamed the sausage, based on the elongated, stretched-out shape its remaining stellar debris traces through the Milky Way's halo. That ancient merger is thought to have significantly reshaped the early Milky Way, puffing up its disk and contributing a large fraction of the stars that now populate its inner halo. In other words, growth through merging and consuming smaller galaxies isn't an unusual chapter in Andromeda's story. It's the normal, expected way large galaxies build themselves up over cosmic history. And the Milky Way carries the same kind of scars, just older ones, harder to spot without the kind of precise, large-scale stellar surveys that have only become possible in the past few years. Andromeda's history is simply more recent, and in some cases, still visible on the sky as an actual stream of stars, rather than something that has to be reconstructed statistically from the motion of individual stars scattered throughout the halo. The gas and dust filling the space between Andromeda's stars carries its own story as well. Radio telescope surveys have mapped out Andromeda's cold gas reservoir in two main forms: a large atomic hydrogen component totaling several billion solar masses spread widely through the disk, and a smaller, denser, molecular component traced through emission from carbon monoxide. That serves as a stand-in for the far more abundant but harder to detect molecular hydrogen, amounting to several 100 million solar masses concentrated in the regions where new stars are actually forming. That gas isn't evenly spread. It concentrates most heavily within the spiral arms and around that off-center ring structure revealed by infrared imaging, exactly the regions where new stars are actively being born. Chemical analysis of Andromeda's stars also reveals what astronomers call a metallicity gradient, meaning stars closer to the galaxy's dense central bulge tend to contain a higher proportion of heavier elements beyond hydrogen and helium. These are forged inside previous generations of stars and scattered back into the surrounding gas when those stars eventually exploded as supernovae. Stars farther out in the disk, and especially within the faint outer halo, tend to be older and chemically simpler, containing far fewer of these heavier elements, a pattern that reflects the galaxy's formation history, with the central regions cycling through many generations of star birth and death much faster than the sparse, slowly evolving outskirts. It's a similar pattern to what's observed in the Milky Way, and it's one of the pieces of evidence supporting the broader idea that spiral galaxies in general grow from the inside out, with dense central regions forming first and outer disks, assembling more gradually over billions of years afterward. Formally, astronomers classify Andromeda as an SA-type spiral galaxy, further refined to SA of type B. On paper, that designation describes a spiral with no obvious large-scale bar, and a moderate tightness to how its arms wind around the core. Tightly wound arms, wrapped closely around the center, generally indicate a different balance of gas, star formation, and gravitational structure than loosely wound, more open arms. And Andromeda's spiral pattern sits somewhere in the middle of that scale, neither as tightly bound as some spiral galaxies, nor as loosely open as others. That classification system, developed originally by Edwin Hubble himself, the same astronomer who first proved Andromeda's true distance, remains one of the basic tools astronomers still use to organize and compare galaxies across the observable universe. And Andromeda, fittingly, was one of the very objects that helped establish it, studied and restudied by generations of astronomers since Hubble's original photographic plates in the 1920s. Despite that official classification, later evidence complicated the picture. The bar itself, that elongated central structure of stars extending outward from the nucleus, wasn't definitively confirmed until relatively recently. For decades, Andromeda's central region appeared to most observers as a simple, smooth, roughly circular bulge. And it took detailed infrared imaging, capable of seeing through obscuring dust, combined with careful modeling of stellar orbits within the bulge during the 2005s, to reveal that the central stars weren't distributed symmetrically at all, but stretched along a preferred elongated axis, the telltale signature of a bar. Bars like this are thought to form naturally within many spiral galaxies over time, as gravitational instabilities within the rotating disk cause stars to settle into elongated, self-reinforcing orbital patterns. And they play an important functional role as well, channeling gas inward from the outer disk toward the central regions, helping to fuel both ongoing star formation near the core over long timescales, the slow feeding of the central supermassive black hole itself. The Milky Way has its own central bar too, discovered and confirmed around the same general period. That means both galaxies destined to merge share this same basic internal architecture, elongated central structures slowly funneling material inward, quietly shaping the long-term evolution of each galaxy from the inside out, long before either one ever draws close enough to affect the other. Scattered throughout that enormous stellar population, among the 1 trillion stars that make up Andromeda's disk, bulge, and halo, are the remnants of countless earlier generations of stars that have already lived out their lives. Based on typical models of stellar evolution, astronomers estimate that a galaxy the size and age of Andromeda should contain somewhere in the range of 100 million stellar mass black holes, the collapsed remains of massive stars that ended their lives in supernova explosions. Alongside those sits a far larger population of neutron stars, the dense, city-sized remnants left behind by slightly less massive stellar collapses, and an enormous number of white dwarfs, the slowly cooling cores left behind by stars like our own Sun once they exhaust their nuclear fuel. Almost none of these objects are individually detectable across 2.5 million light-years. Since most stellar remnants emit little or no light on their own, revealing themselves only indirectly through their gravitational effects on a visible companion star or through the brief, energetic bursts produced on the rare occasions when two of them collide or merge. It's a quiet reminder that the trillion stars we count when describing Andromeda represent only the currently shining population. They're layered on top of an even larger, mostly invisible graveyard of stars that finished burning long ago, drifting silently through the same disk, tracing the same slow orbit around the same distant, hungry black hole at the center. Upcoming observational efforts promise to sharpen this picture even further. The European Space Agency's Euclid mission, launched in 2023, is designed in part to map the distribution of matter, including dark matter, across enormous volumes of space. And its wide field imaging capabilities make it well suited to studying the extended, faint structures surrounding galaxies like Andromeda, including satellite systems and stellar streams too dim for most earlier surveys to capture in full detail. The Vera Rubin Observatory in Chile, beginning its major sky survey operations in the mid-2020s, is expected to catalogue faint stars and structures across Andromeda's outer halo, with far greater completeness than previous ground-based efforts managed. It could reveal additional satellite galaxies, additional tidal streams, and a more precise picture of exactly how much dark matter surrounds the galaxy and how it's distributed. Each of these future observations builds on everything that came before, from Al-Sufi's little cloud to Hubble's Cepheid variables to Gaia's precise motion measurements, adding another layer of detail to an object that, despite nearly a century of intense study, still isn't fully mapped or fully understood. It's natural to wonder whether anyone might be looking back. With an estimated 1 trillion stars, many of them presumably hosting planets of their own, Andromeda represents an enormous number of potential locations where life, and perhaps intelligence, could theoretically have arisen at some point across its long history. In practice, detecting any of that from Earth is essentially impossible with current technology. Even the most powerful telescopes available today struggle to directly detect individual exoplanets orbiting stars within our own galaxy, let alone stars within a separate galaxy 2.5 million light-years away, where even the brightest individual stars are difficult to resolve at all. Searches for artificial radio signals, the traditional method used by projects like the Search for Extraterrestrial Intelligence, face an even steeper challenge across that kind of distance. Since any signal would need to be extraordinarily powerful, deliberately aimed, and would still take 2.5 million years to arrive, meaning whatever civilization sent it would have needed to do so. Around the same time, our early human ancestors were first learning to walk upright on the African savanna. None of this rules out the possibility of life within Andromeda. It simply places that question, for now, firmly outside the reach of any answer we could actually obtain. Andromeda remains, in that sense, a galaxy of trillion-fold possibility and complete observational silence at the same time. A reminder of how much of the universe exists entirely beyond our current ability to examine closely, no matter how curious we are about what might be out there. Studying Andromeda's structure, its history of mergers, its central black hole, and its slow transformation toward an eventual collision with our own galaxy also matters for a much broader scientific reason, beyond simple curiosity about one particular neighbor. Large elliptical galaxies, the kind of galaxy Milky is expected to eventually become, are extremely common throughout the observable universe. And astronomers have long understood that most of them likely formed through exactly this kind of process. Two or more large spiral galaxies colliding and merging together over billions of years. Because Andromeda is close enough to study in this level of detail, it offers one of the clearest, most complete case studies available anywhere for understanding how that broader transformation actually happens, step by step. That beats simply inferring it from the end results, visible in distant, already merged, elliptical galaxies scattered across the universe. That includes its past mergers, visible in structures like the giant stellar stream and the stripped remnant of M32, and its future merger with the Milky Way, precisely modeled using Hubble and Gaia motion data together. In that sense, Andromeda functions as a kind of open textbook, a single nearby example detailed enough to test and refine the models astronomers apply to galaxy evolution everywhere else, in galaxies far too distant and too faint to ever study with this same level of precision. Looking beyond even the Milky Way and Andromeda merger itself, there's a longer story still unfolding across the universe as a whole. One that touches on why events like this even happen at all, and why, eventually, they'll stop happening entirely. The universe is expanding, and that expansion is accelerating, driven by something astronomers call dark energy, a mysterious property of space itself that's gradually pushing distant galaxies apart from each other at an ever-increasing rate. Galaxies that are gravitationally bound together, like the members of our local group, aren't pulled apart by this expansion, because the mutual gravity holding them together is currently strong enough to overcome it at these relatively close distances. But galaxies outside our local group, the countless other galaxies scattered across the wider universe, are being carried away from us by that expansion. And over enormous timescales, tens of billions of years and beyond, most of them will eventually become too distant and too redshifted to detect at all. Milkdromeda, the eventual merged product of our own galaxy, and Andromeda, will likely remain gravitationally bound to whatever else survives within the local group, but increasingly isolated from the rest of the universe as everything farther away drifts beyond the reach of observation. Some cosmologists describe this as a kind of long, slow cosmic isolation, a future in which whatever observers might still exist within Milkdromeda, however unlikely that is, would eventually look out at a sky containing only their own merged galaxy and a handful of gravitationally bound neighbors. Essentially, nothing else would be visible at all, the rest of the universe having expanded beyond the horizon of what light could ever again reach them. That's an almost unimaginably distant future, far beyond even the 7 billion years or so it will take for the Andromeda merger itself to complete. But it's part of the same long arc, the same slow unfolding of gravity and expansion working against each other across cosmic time. That begins, for us, with that single approaching galaxy visible right now as a faint smudge in the autumn sky. There's something worth sitting with in all of this. Imagine, for a moment, what it would actually be like to travel through Andromeda's disk itself, rather than observing it from 2.5 million light-years away. Despite containing 1 trillion stars, the experience wouldn't feel crowded at all. The average distance between neighboring stars within a galaxy like Andromeda is measured in light-years, several light-years typically. That means a traveler moving through the disk would spend the overwhelming majority of their journey surrounded by nothing but dark, empty space, with individual stars appearing as distant, isolated points of light, rarely bright enough to illuminate anything nearby. Only near the crowded central bulge, or within one of the dense star-forming regions like NGC 206, would the sky begin to feel genuinely full. It would be packed with far more visible stars than anything ever seen from Earth. Entire clusters of brilliant young stars lighting up surrounding clouds of gas and dust in shades of red and blue. Passing near the galactic center itself, close to the supermassive black hole anchoring the whole structure, stars would move visibly against each other over the course of just a few human lifetimes, orbiting far faster than anything in our own solar neighborhood, caught in the grip of that immense, concentrated mass. It's a useful corrective to how galaxies often get imagined, as tightly packed swirls of light with barely any room between the stars. The truth is closer to the opposite. A galaxy, even one containing 1 trillion stars, is mostly emptiness. vast stretches of near-total darkness, punctuated occasionally by the isolated glow of another sun, another possible solar system. It's another quiet corner of a structure so large it takes light itself 220,000 years just to cross from one side to the other. For most of human history, people looked up at that faint smudge in the night sky and had no idea what they were seeing. A cloud, maybe. A strange star, maybe. Something within our own small corner of the universe, certainly. Because for most of history, nobody imagined the universe extended much beyond what the eye could see. It took centuries of careful observation, from Al-Sufi's little cloud, to Marius's candle flame through Horn, to Huggins's spectrum, to Slipher's blue shift, to Leavitt's pulsing stars, and eventually the work of Edwin Hubble in the early 20th century, to reveal that this faint patch of light was in fact an entire galaxy. Its own island of stars, spinning slowly 2.5 million light-years away, containing more stars than most people could imagine, even trying to count. And now we know even more. We know its size, its mass, its structure, its satellite galaxies, the supermassive black hole anchoring its core, the scars of galaxies it has already consumed, and the slow, patient trajectory that will eventually bring it face to face with our own galaxy, billions of years from now. The scale of it is difficult to hold on to. 220,000 light-years across. 1 trillion stars. 460 globular clusters. A collision course billions of years in the making. Numbers so large, they stop feeling like numbers at all and start feeling more like a kind of humility, a reminder of just how small our own perspective really is. Standing on a single planet, orbiting a single star, inside a galaxy that is itself just one of billions. Andromeda has been there this entire time, quietly approaching, long before anyone on Earth knew what it was. And it will still be approaching long after all of us are gone, indifferent to our timelines, moving according to nothing but gravity and time. Think back to Al-Sufi, recording that little cloud in the year 964, with no instrument capable of showing him anything more than a faint smear of light. He couldn't have known that the smear he was so carefully documenting was already, at that moment, 110 kilometers closer to Earth than it had been the year before. And the year before that, quietly closing a gap that had already been narrowing for millions of years before he was ever born, and would keep narrowing for billions of years after his own civilization had faded into history. Every single person who has ever looked up and noticed that faint smudge across 1,000 years of recorded observation was looking at an object already in motion toward us, whether or not they had any way of knowing it. The stars we associate with permanence, the fixed backdrop against which everything else in the sky seems to move, aren't fixed at all. They're simply moving on timescales, too slow, too vast, for a single human lifetime to notice directly. A star's apparent stillness is really just an illusion produced by the mismatch between how long a person lives and how long it actually takes for anything in the sky to visibly shift position. Andromeda's approach is the same kind of motion, just easier to measure and easier to project forward. Because unlike most of the faint points of light scattered across the night sky, we've had the tools, for about a century now, to actually track its spectrum, its shifting light, and calculate exactly where that motion is heading. It's worth remembering, too, just how recent all of this understanding actually is. For the overwhelming majority of the roughly 300,000 years modern humans have existed, nobody knew galaxies existed at all, let alone that one was approaching our own. That knowledge is barely a century old. A thin, recent sliver, layered on top of thousands of generations who looked at the exact same sky, saw the exact same faint smudge, and had absolutely no framework for understanding what it actually was. In that context, the story of Andromeda isn't just a story about a distant galaxy. It's a story about how quickly human understanding can expand once the right tools and the right questions finally come together. It's a story about how an object that spent 1,000 recorded years as an unexplained little cloud could, within the span of a single human lifetime, be measured, mapped, weighed, and projected forward across billions of years with genuine scientific confidence. That's not a small achievement. It's one of the clearest examples available of how much can be learned about the universe from a single planet, using nothing but light that's already arrived, patiently gathered and interpreted by people willing to ask careful, persistent questions about a faint smear of light that most of history simply looked past. There's a certain peace in that, if you let yourself sit with it. The universe doesn't need us to understand it in order to keep unfolding. It simply does. And every clear night, that faint smudge of light is still up there, patiently waiting for anyone willing to look up and actually see it for what it is. Not a smudge, not a cloud. A galaxy vast beyond easy comprehension, drifting slowly toward a future that will eventually reshape the sky itself. Thank you for joining me tonight to explore the true scale of Andromeda. From that faint smudge our ancestors mistook for a little cloud, to the trillion-star galaxy we understand it to be today, and the slow, inevitable collision that awaits it and our own Milky Way, billions of years from now. If this exploration gave you a new sense of scale, or made you look at that faint patch of light a little differently, a like or a subscribe would mean a lot. It helps this channel keep making these deep dives into the cosmos. And the next time you find yourself under a truly dark sky, take a moment to look for that faint smudge north of the great square of Pegasus. What you're seeing isn't small. It only looks that way from 2.5 million light years off. Good night.